So we know now friction have two types. There is the static friction and there is a dynamic or kinetic friction. In this lecture we will talk about kinetic friction and how does it affect the motion of things. We have the same example of table that we talked about last time. If you remember about static friction, we said while you're trying to push the table, you apply a force. The table doesn't go anywhere until the moment where the table would start to move. That is all called static friction. That is resisting your force to be able to keep the table stable in its place. For kinetic friction, we have a person who's applying a force to the table. That friction starts when the moment the table starts moving as effect of the applied force. So same analysis as we did before. There is applied force with a certain angle of theta reference to the x-axis. It has an x component of F applied x and F applied y. And we mentioned before F applied x can be by the trigonometry that we learned, that F applied multiplied by cosine theta, and F applied on the y is F applied multiplied by sine theta. And the kinetic friction force is being to the left on the x-axis against the x component of the force in this case. Now in many cases we have objects on inclined surface. When the object is inclined surface, we said he could be stand still in his place and having static friction, and he could be moving. In this case you would start to see the kinetic friction force applied to the moving object. So here if we take a free body diagram for a box sitting on inclined surface, the surface is inclined with an angle of theta. That's the angle right here. Then we have the regular forces. We have the gravitational force pulling downwards, and there's the normal force pulling perpendicular to the inclined surface. And here the gravitational force is having an angle of theta. And we said we set the, instead of using the Cartesian to make life simple, we set anything or any force parallel to the inclined surface is a parallel force. Any force perpendicular is considered a perpendicular force. It's like you're setting the x-axis to be parallel to the surface of inclination and the y-axis to be perpendicular to the surface of inclination, just to make life easy as solving related problems. So we can see here there is the parallel gravitational force pulling the object downward on the inclined surface, and the kinetic friction energy or friction force here is pulling backward against the motion of the object, trying to stop the object from moving. Now when you have an object on an inclined surface, this object could be, of course it is in motion since we're talking about kinetic friction, this object could be either accelerating downwards or accelerating upwards. To talk about an object accelerating downwards, of course, as he is accelerating downwards as effect of his weight or effect of the parallel gravitational force, then you will see an opposite force pulling the object upward, which is the friction, the kinetic friction force in this case, trying to stop him from moving. If we want to analyze the motion of that object, there is parallel forces and perpendicular forces. Before we were talking about x-axis forces and y-axis forces. In this case, parallel and perpendicular forces. We have the gravitational force parallel pulling downwards, and we have the kinetic friction force pulling upward, and you can see the direction of the net force on the parallel axis is pulling downward. Of course, something to remember, in this case the net force is not zero on the x-axis, and in many cases not zero on the y-axis, or it's not zero on the parallel axis. You need to pay attention if there is any motion on the perpendicular axis. Before we were saying the parallel net force is zero because the object is stand still. We know there's only static friction in this case. While in kinetic friction there is a motion for sure, so the net force on the parallel direction is not zero. So when you analyze the net force for the parallel direction, you would say the gravitational force parallel plus the kinetic force, and the F net would be represented as the mass by the acceleration, which equals the gravitational force parallel plus the kinetic friction force. For the parallel forces, we say the F net parallel would equal the normal force plus the gravitational force perpendicular So the F net perpendicular equals the normal force plus the gravitational force perpendicular. In this case, the perpendicular direction, there is no motion for that object. It's only moving on the parallel direction. So the F net perpendicular would be Fn plus the Fg perpendicular. We don't say Fn perpendicular because it is perpendicular in all cases or all the time. F net perpendicular is 0. In this case, we can conclude that the normal force equals minus the F gravitation perpendicular. Now, when we have a kinetic friction, when we have an object accelerating upwards, the free body diagram would look like this. There's applied force upward, and the kinetic force would be, or kinetic friction force would be downwards. And from analyzing the gravitation force, you have the gravitation force parallel would be pulling downward. Normal force would be perpendicular on the inclined surface, and the perpendicular component of gravitation force will be pulling downwards relative to the inclined surface. We analyze vector analysis for the forces. You will find out that the net parallel force would be pulling upwards, competing with the gravitational parallel force pulling downwards, and the kinetic friction force pulling downwards, and the applied force pulling upwards. F net parallel is not 0 as well in this case. F net perpendicular is 0. So in this case, we can say that the normal force equals the minus F gravitation perpendicular. And for the F net parallel, we can analyze the forces and replace F net parallel with mass multiplied by acceleration. And you compensate the values given to you in the problem, and you will be able to find the final solution. We have an example here on kinetic friction force. There is a 3.5 kilograms block sliding down an inclined surface which is inclined in 15 degrees. The surface of the incline exerts a force of kinetic friction of magnitude 3.9 newtons on the block. Calculate the acceleration of the block. So you have a block 3.5 kilograms in weight on inclined surface 15 degrees. The object will be accelerating downwards in this case. You're given m, you're given theta, you're given g, that we know, and you're given the kinetic friction force 3.9 newton. He needs the acceleration of the block. Let's draw a free body diagram first. If you do a free body diagram, then you can see here setting up directions. Uphill is positive in this case, upwards is positive in this case, and down is negative. Uphill is negative, downhill is positive. As we mentioned before, you can set any convention you want as long as it serves the purpose and you keep consistent in the solution along your solution for that problem. So we have normal force upwards to the inclined surface. You have gravitational force on the true y-axis. Then you have the theta over here, which is the same as here by trigonometry. And you do the x and y components. You can set up a separate analysis for the parallel forces and for the perpendicular forces. So you can see here in the perpendicular direction, the F net perpendicular equals the F normal plus the F gravitation perpendicular. We know there is no perpendicular motion. That means F net perpendicular is 0, so the F normal equals minus the F gravitation perpendicular. For the parallel direction, you have the F net parallel equals the F gravitation parallel plus the kinetic friction force. F net can be replaced as mass by acceleration. Fg parallel is known, kinetic friction is known, so the Fg parallel would be mg sine theta. Mass by acceleration equals the mg sine theta plus minus the 3.9 newtons of kinetic friction force. And replace m, replace g, replace theta. You'll be able to find a to equal 9.81 multiplied by sine 15 minus 3.9 over 3.5 kilograms. That would give you 1.4 meters per second squared downhill. That would be the acceleration of the object on an inclined surface. Now, if you want to look at a graph for static versus kinetic friction, in this case, we can draw time versus the magnitude of the force of friction in Newton. We can see here the curve would be represented as there is a curve for static friction. You are pulling a force, but there is a friction building up until it reaches a breaking point where that is the maximum value of static friction. After that, the object will start to move, and all the friction that you get is a kinetic friction. And it's something to mention and to keep in mind. Often the magnitude of F kinetic is less than the magnitude of F static. So, of course, you need to overcome the static friction to be able to have motion, which means to have kinetic friction. So it always makes sense that the magnitude of the kinetic friction is less than the magnitude of static friction. Otherwise, the object will always be in static friction.